Tonight, we're going to take a hard look at the planet we've been calling our next-door neighbor, Mars. You've heard it described as the most reachable destination in the solar system. The obvious next step, the planet humanity is going to colonize. And if you've spent any time following space news, you've probably absorbed the idea that Mars is close. Close enough that we send spacecraft there regularly. Close enough that Elon Musk talks about it like a commute. Close enough that it feels like the frontier is practically within reach. Here's the thing most people don't realize. That feeling is an illusion. A comfortable one, carefully maintained by decades of mission announcements, science fiction, and a single extraordinary night in August 2003 when Mars genuinely was closer than it had been in 60,000 years. But that moment, that one exceptional alignment, lodged itself into the public imagination as a baseline, as if that's how close Mars usually is. It isn't, not even close. Think about that for a second. The closest Mars has ever come to Earth in all of recorded human history is 34.8 million miles. And the average distance, the number that actually governs how space agencies plan missions, calculate fuel loads, and schedule launch windows, is 140 million miles. That's roughly 1.5 times the distance from Earth to the Sun. That's not next door. That's not even the same neighborhood. Now, does this matter? You might be thinking that the distance is just a number, that engineers account for it, that spacecraft handle it, that it's a logistics problem and not a fundamental barrier. But here's the thing. The distance to Mars is not just a number. It determines how long it takes to get there. It determines how long you have to wait between chances to launch. It determines how many minutes, sometimes more than 20, pass between sending a message to a rover and receiving a response. It determines how much radiation a crew absorbs in transit. It determines whether a rescue mission is even theoretically possible if something goes wrong. The distance is not a detail. The distance is everything. And yet the story we tell ourselves, the comfortable version, is that Mars is nearby, that it's accessible, that we're essentially ready to go, just waiting on the funding and the political will. That story is appealing because it makes the future feel close. It makes the dream feel manageable, but it papers over a reality that is far more extreme than most people have ever been asked to reckon with. Space agencies understand this. The people designing Mars missions understand this. But the gap between what engineers know and what the public believes is enormous. And that gap has consequences for how we fund exploration, for how we evaluate timelines, for how seriously we take the engineering problems that need to be solved before a human being sets foot on Martian soil. So tonight, we're going to close that gap. We're going to look at what the distance to Mars actually is, not the record-close approach, not the optimistic figure that gets quoted in headlines, but the full range, the closest, the farthest, the average. We're going to look at why that distance is never the same twice, why the window to launch opens and closes every 26 months, and what it actually means for the human beings who will one day make that journey. The communication delays, the radiation, the isolation of crossing 140 million miles of empty space with no possibility of turning back. By the time we're done, you're going to understand exactly why calling Mars our nearest neighbor isn't just imprecise. It's a comfortable lie we've been telling ourselves for a long time, and the reality underneath it is far more sobering and far more interesting than the simplified version. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Let's begin with what you currently think about Mars. You've probably heard it described as our nearest neighbor in space, the next step for humanity, the planet we're going to. And if you follow space news at all, you've seen the mission announcements, the rover landings, the SpaceX renders of gleaming silver rockets descending toward a rust-colored horizon. Mars feels close. Mars feels almost within reach. Here's the thing most people don't realize. That feeling has a very specific origin, and it has almost nothing to do with the actual distance. It starts with August 2003. That summer, Mars made its closest approach to Earth in nearly 60,000 years. The two planets came within 34.8 million miles of each other, a number that sounds almost manageable until you start thinking about what 34.8 million miles actually represents. But the coverage wasn't about scale. The coverage was about proximity. Mars was closer than it had been since Neanderthals roamed Europe. Telescopes sold out. Astronomy clubs reported record attendance. Every major news outlet ran the story. And something happened in that moment that is very hard to undo. The number lodged in public memory as a kind of baseline. People who read those articles in 2003 came away with an impression of Mars as a place that is, relatively speaking, right there. And that impression has persisted. Think about that for a second. An event that won't repeat until the year 2287 became the mental reference point for how far away Mars is. That's where it starts. But it doesn't stop there. Mars missions launch roughly every 2 years. Every 26 months, when the orbital geometry lines up correctly, space agencies send spacecraft toward Mars, and the launches get covered. The Curiosity rover, Perseverance, the UAE's Hope orbiter, China's Tianwen-1. Each launch is a news cycle, a moment of public excitement, and each one reinforces the same implicit message. We go to Mars regularly. Therefore, Mars must be accessible. The cadence of missions creates a sense of routine. We have rovers on Mars right now. We can watch them drive across the surface. Scientists on Earth are directing a vehicle on another planet, and the whole thing feels almost ordinary. That ordinariness is the misconception at work. The launches happen every 2 years, not because Mars is easy to reach, but because that's how often the orbital window opens at all. Miss the window and you wait another 26 months. That's not routine access. That's a narrow gate that opens on its own schedule and closes quickly. Then there's popular culture. The Martian came out in 2015, and it was brilliant, well-researched, technically serious, and it put a human face on a Mars mission in a way nothing had before. But what audiences took away, more than anything else, was a sense of plausibility. If Matt Damon could survive on Mars long enough to be rescued, Mars couldn't be that far gone from human experience. SpaceX has spent years releasing architectural renders and timelines that describe Mars colonization in language borrowed from real estate development. A city of 1 million people. Reusable rockets, a self-sustaining civilization. The framing is ambitious but confident, and confidence is contagious. NASA press releases describe Mars as the next destination for human exploration. Presidential directives have named it as a national goal. The drumbeat from every credible institution is the same. Mars is where we're going next. None of that is dishonest. But it shapes perception in ways that the raw numbers don't support. Here's something most people never question. When we say Mars is our nearest planetary neighbor, we are factually wrong. Venus is closer to Earth on average, not by a little, by a wide margin. The average distance between Earth and Venus at closest approach is around 25 million miles. Mars, on average, sits about 140 million miles away. Even at Mars's all-time record closest approach in 2003, the two planets were still 34.8 million miles apart, farther than Venus typically gets at its nearest. Venus approaches Earth more closely, more regularly, and far more predictably than Mars ever has. So why does nobody talk about going to Venus? Because Venus is, in almost every practical sense, a hellscape. Surface temperatures that melt lead, atmospheric pressure 90 times what we experience on Earth, clouds of sulfuric acid. There is nothing welcoming about Venus, and so it gets ignored in the public conversation about human spaceflight, while Mars, with its ancient river valleys and polar ice caps and day length of 24 hours and 37 minutes, captures the imagination. Mars is easier to romanticize. Mars has seasons. Mars has a surface you could theoretically stand on. And so the narrative has settled around Mars as the destination, and with it, an unspoken assumption that Mars must be nearby. Because why else would it be the target? That reasoning runs backwards. Mars is the target not because it is close, but because it is the least hostile nearby option, which is a very different thing. The decision to aim for Mars is about conditions, not distance. But the public perception collapsed these two things into one. What gets lost in all of it, the 2003 coverage, the biannual launches, the mission renders, the blockbuster films, is any real reckoning with what 140 million miles means. Not as a number, as a physical reality, as travel time, as communication delay, as the gap between Earth and a crew that has no way back until the orbital geometry permits it. And that comfortable idea, Mars as close, Mars as reachable, Mars as the obvious next step, is what we need to examine very carefully. The distance between Earth and Mars was first measured with real precision in 1672, and the method Giovanni Cassini used was almost absurdly simple in concept. He split the observation in two. Cassini stayed in Paris. He sent a fellow astronomer, Jean Richet, all the way to French Guiana, roughly 5,000 miles south. On the same night, both men looked at Mars against the background of stars. And here's the thing most people don't realize. Mars appeared in a slightly different position depending on where you were standing on Earth. That tiny shift, that apparent displacement against the fixed stars, is called parallax. You've experienced it yourself. Hold your finger up, close one eye, then switch to the other. Your finger seems to jump. That's parallax. The closer the object, the bigger the jump. Cassini and Richard did exactly this with an entire planet, and from the size of that angular shift, they calculated how far away Mars actually was. Think about that for a second. No radar, no satellites, no atomic clocks. Two men on opposite ends of the Earth looking at the same object on the same night, and from the difference in their observations, they worked out a distance of tens of millions of miles. The result Cassini got was remarkably close to what we know today, off by only about 7% in 1672. That's not a rounding error, that's extraordinary. Modern measurements are a different thing entirely. Today we use radar ranging. We fire a radio signal directly at Mars, it bounces off the planet's surface, and we time exactly how long it takes to come back. Radio waves travel at the speed of light, about 186,000 miles per second. So if you know the travel time down to a fraction of a millisecond, you can calculate the distance with extraordinary precision. We're talking accuracy within a few hundred meters over distances of hundreds of millions of miles. That's the equivalent of knowing the exact length of a football field while standing on the opposite side of the country. But here's where the measurement gets complicated, and this is where most explanations quietly skip over something important. The distance between Earth and Mars is never the same twice. Not from one year to the next, not from 1 month to the next, not even from one day to the next. Every time we measure it, we get a different number. And that's not a failure of the measurement. That's the reality of the distance itself. At its closest, Mars has come within 34.8 million miles of Earth. That happened in August 2003, an approach so rare it hadn't occurred in nearly 60,000 years. At its farthest, when Mars swings around to the opposite side of the Sun from Earth, the distance stretches past 250 million miles. You're looking at a range that goes from 34.8 million miles on one end to more than 250 million miles on the other. That's not a small fluctuation. That's a factor of more than 7. The farthest Mars can get from us is more than 7 times farther than the closest it ever gets. And between those two extremes, the distance is always moving, always somewhere on that vast spectrum, shifting every single day. This is why the measurement itself is so deceptively tricky. Cassini got a number in 1672, but that number was only accurate for that specific night. A year later, the distance would have been different. 6 months earlier, it would have been different again. There is no single answer to the question of how far away Mars is. There's only ever a current answer, valid right now, already slightly wrong by tomorrow. The reason for all of this is something we'll get into much more deeply in a moment, but the short version is this. Earth and Mars are both orbiting the Sun, and neither orbit is a perfect circle. They're ellipses, stretched ovals. Earth moves faster than Mars. Mars's orbit is noticeably more egg-shaped than Earth's. The two planets are constantly moving relative to each other, sometimes pulling close, sometimes drifting apart. And the geometry never repeats exactly the same way twice in any human lifetime. That's what's driving the range. That's why one measurement gives you 34.8 million miles and another gives you 250 million. If you average out the distance across the full range of positions, every point where Mars has been relative to Earth over time, you land on a number of about 140 million miles. That's the figure astronomers use when they talk about how far away Mars typically is. 140 million miles. For context, the distance from Earth to the Sun is about 93 million miles. So Mars, on average, is more than 1.5 times farther from us than the Sun. Not the close neighbor, not the easy hop. 1.5 times beyond the Sun. What that number actually means, 140 million miles as an average with the real distance swinging wildly above and below it, is where things start to get uncomfortable. To understand why Mars's distance from Earth is never the same twice, you have to understand how orbits actually work. Most people picture the planets moving in neat circles around the Sun, clean, regular, predictable. That picture is wrong. Every planet in our solar system travels in an ellipse, a stretched oval, with the Sun sitting not at the center but at one of 2 focal points offset from the middle. That single fact changes everything about how we think about planetary distances. The Sun isn't centered in the orbit, it's shifted toward one end, which means the planet moves closer to the Sun during part of its journey and farther away during another part. Every orbit is, at its core, a constant approach and retreat. This is what Johannes Kepler worked out in the early 1600s. He had spent years staring at the meticulous observations of Tycho Brahe, trying to force the data to fit a circular model, and it simply wouldn't work. The numbers kept fighting him. When he finally allowed the orbits to be ellipses, everything fell into place. Kepler's first law states it plainly. The orbit of a planet is an ellipse, with the sun at one focus. His second law tells you that a planet moves faster when it's closer to the sun and slower when it's farther away. Those two laws together are the foundation of why Mars's distance from Earth is never constant. The planets aren't just moving, they're moving at speeds that change depending on where they are in their orbits. Here's the thing most people don't realize. Earth and Mars are both doing this simultaneously, and their ellipses are not the same shape. Earth's orbit is nearly circular. Its eccentricity, the measure of how stretched the ellipse is, where 0 is a perfect circle and 1 is a flat line, is about 0.017. That's almost nothing. Earth's orbit barely deviates from a circle. Mars is a completely different story. Mars has an orbital eccentricity of 0.0935. That's the second highest of any planet in the solar system, behind only Mercury. Think about what that means practically. Mars swings between about 128 million miles from the Sun at its closest point, and roughly 154 million miles at its farthest. That's a swing of about 26 million miles just in Mars's distance from the Sun alone. Earth, by comparison, barely moves between 91 and 95 million miles from the Sun across its entire orbit. Mars's path is genuinely, noticeably oval. Now picture both planets moving at the same time on their different tracks. Think of it like two cars on a racetrack, but the track has two lanes and neither lane is circular. Earth is on the inside lane and it moves faster. Earth completes one full orbit in about 365 days. Mars, on the outside lane, takes 687 days, nearly 2 Earth years, to go once around. Earth is lapping Mars, but because neither track is a circle, the distance between the two cars isn't just a function of how far ahead or behind one is on the track. It also depends on exactly which part of the oval each car is currently driving through. Sometimes Earth is on the part of its track that curves toward Mars's track. Sometimes Mars is on the far end of its stretched oval, swinging out away from the Sun and away from Earth at the same time. The combination of those two positions, both changing every single day, is what produces the distance between the two planets at any given moment. The time it takes for Earth to lap Mars, to go from one point where they're lined up on the same side of the Sun all the way around until they're lined up that way again, is called the synodic period. For Mars, that's approximately 780 days, a little over 26 months. That's the number that drives the opposition cycle. Every 26 months or so, Earth catches up to Mars and passes between Mars and the Sun. That's opposition, and it's the moment when Mars is closest to Earth for that particular cycle. But here's where it gets important. Because both orbits are ellipses, not circles, not every opposition puts the planets the same distance apart. If Mars happens to be on the part of its oval that swings closest to the Sun when Earth passes it, the two planets can be extremely close, tens of millions of miles. If Mars is on the far side of its oval, swinging away from the Sun, that same opposition can find the planet separated by 60 or 70 million miles. Same event, very different distances. The geometry of the two ellipses determines everything. You can see this play out when you look at actual opposition distances over the years. They vary enormously. Some oppositions are exceptionally close. Others, while still called oppositions, find Mars far enough away that even a good telescope barely resolves the disk. The 26-month cycle gives you the timing of the event. The shape of the ellipses and the positions within them give you the distance. Those are two separate things, and confusing them is one of the most common mistakes in how people think about Mars. Every single day, Earth moves about 1.6 million miles along its orbit. Mars moves about 860,000 miles along its orbit. The gap between them, the actual straight-line distance across space, changes every day as a result. Some days the gap narrows by hundreds of thousands of miles. Some days it widens. There's no fixed rate, no constant approach or retreat. It depends entirely on the geometry of both orbits at that specific moment in time. And because of that constantly shifting geometry, 2 planets, 2 ellipses, 2 different speeds, the distance between Earth and Mars is never fixed, never predictable without calculation, and never as simple as it looks on a diagram. The closest Mars has ever come to Earth in recorded human history happened on August 27, 2003. That night, the 2 planets were separated by just 34.8 million miles, 56 million kilometers. And here's what most people don't realize about that number. It hadn't happened in 60,000 years. Not since 57,617 BC had Mars been that close to Earth. No one in all of recorded human civilization had ever witnessed an approach like that before. The telescopes of Galileo never caught it. The astronomers of ancient Greece never saw it. Every human being who had ever looked up at that reddish point of light in the night sky had seen it from farther away than we did in August 2003. Think about that for a second, and it won't happen again until 2287. Anyone alive today will never see Mars that close again. Their children won't. Their grandchildren won't. The next time Earth and Mars close to that distance, it will be 284 years from now, longer than the United States has existed as a country. Now, here's where things get even more interesting. That record-breaking 34.8 million miles wasn't even the theoretical minimum. According to the geometry of the 2 orbits, the absolute closest Mars and Earth could ever get is 33.9 million miles, about 54.6 million kilometers. That would require a very specific alignment. Mars at perihelion, the closest point in its orbit to the Sun, and Earth simultaneously at aphelion, the farthest point in its own orbit. Those 2 conditions have to coincide at the exact moment Earth passes between Mars and the Sun. That alignment has never occurred in recorded history, not once. The 2003 approach came close, but not close enough. We got to 34.8 million miles, and even that was a once-in-60 millennia event. The true theoretical minimum remains something humanity has never actually witnessed. But let's talk about the other end of the scale. Because while 34.8 million miles sounds relatively manageable, at least by cosmic standards, the maximum distance between Earth and Mars is something else entirely. At conjunction, when Mars passes behind the Sun and the 2 planets are on opposite sides of the solar system, the separation reaches over 250 million miles. That's 401 million kilometers. Mars doesn't just look dim from that position, it disappears into the Sun's glare entirely, invisible from Earth, unreachable for communication, sitting on the far side of a star. So you have 2 extremes. 34.8 million miles at the closest recorded approach, and 250 million miles at the farthest. The ratio between those 2 numbers is more than 7 to 1. The same planet in the same solar system can be 7 times farther away depending purely on where both worlds happen to be in their orbits at that moment. That's not a minor fluctuation. That's not the kind of variation you can round off and ignore. Here's where the numbers become genuinely uncomfortable. Look at what's happened to Mars's closest approach distance just in the last few oppositions. In July 2018, Mars came within 35.78 million miles of Earth, exceptionally close, almost as good as 2003. People with backyard telescopes could see surface features. It was a genuinely remarkable viewing window. Then, in December 2022, that closest approach distance had grown to 50.61 million miles. That's not a slightly worse opposition. That's 15 million miles farther, a gap roughly equivalent to 60 times the distance from Earth to the Moon, added on top of what 2018 offered. In January 2025, the number climbs further still, 59.70 million miles. Then, in February 2027, 63.01 million miles. Look at that progression. 35.78 million, 50.61 million, 59.70 million, 63.01 million. Each of those is a Mars opposition, a moment considered favorable, a moment when Earth has lapped Mars and sits between it and the Sun. And yet the distances span a range of nearly 30 million miles just across 4 consecutive oppositions. By 2027, even at closest approach, Mars will be nearly twice as far away as it was during the historic 2003 encounter. What drives that progression? It comes back to the orbital mechanics we covered earlier. Not all oppositions are created equal. When Earth passes Mars while Mars sits near its own perihelion, near its closest point to the Sun, you get a 2003-style approach. When opposition happens while Mars is closer to its aphelion, the far end of its orbit, you get a 2027-style approach. 2 planets, 2 ellipses, and the timing of their intersection determines everything. Most people who saw the news coverage in 2003 walked away with the impression that Mars is relatively close. And in 2003, it was. But that impression has been locked in public memory as a baseline, as though 34.8 million miles represents something typical. It doesn't. It represents the best approach in 60,000 years of Earth history. When you plan a spacecraft mission, you don't get to plan it for 2003. You plan it for the window that's actually available, which might look a lot more like 2027. And that variability, that wild swing from 34.8 million miles to 250 million miles, changes everything about how you fly there, how long the trip takes, how much fuel you burn, and how long your signals take to travel. The distance to Mars isn't a fixed number you can memorize and apply. It's a moving target that shifts every single day, and the difference between the best case and the worst case is measured in hundreds of millions of miles. That 7-to-1 swing between closest and farthest isn't just an astronomical curiosity. It has direct, practical consequences for every mission we've ever sent to the Red Planet. There's a specific moment in the orbital cycle, opposition, that more than anything else shapes how we experience Mars from Earth. Here's what opposition actually means. Earth orbits the Sun faster than Mars does. We complete 1 lap in 365 days. Mars takes 687 days. So Earth is constantly lapping Mars, like a faster runner on the inside lane of a track. Roughly every 26 months, Earth catches up and passes Mars. And for a brief window, the 3 bodies align, Sun, Earth, Mars, in a straight line, with Earth in the middle. That alignment is opposition. At that moment, Mars rises in the east exactly as the Sun sets in the west. It's visible the entire night, reaching its highest point in the sky around midnight. It's also, in most cases, at its brightest and its largest in the eyepiece of a telescope. This is what astronomers mean when they say conditions for observing Mars are favorable. This is what space agencies are looking at when they plan their launch windows. Opposition is the centerpiece of the entire Earth-Mars relationship. But here's the thing, most people don't realize about opposition. It is not the same as closest approach. not automatically. The moment when Earth and Mars are geometrically lined up with the Sun does not have to be the same moment when the two planets are physically nearest to each other. Because both orbits are ellipses, not perfect circles, the geometry is never that clean. The actual closest approach, the moment of minimum distance, can occur a few days before opposition or a few days after it, depending on where each planet sits on its respective ellipse at that particular time. During the 2003 opposition, for example, the geometric alignment and the closest approach were separated by about 2 days. That gap matters because it reminds us that opposition is a useful marker, not a precise measurement. The real number, the actual mileage between the two planets, requires a calculation, not just an observation of when Mars appears in the sky. Still, opposition is the event that defines how we experience Mars. During opposition, the planet can look dramatically different from how it appears at other times in the cycle. At a favorable opposition, Mars is unmistakable in the night sky, bright reddish-orange, impossible to confuse with a star because it doesn't twinkle. Amateur astronomers can make out surface features through a decent backyard telescope. The polar ice caps become visible. Dark regions of ancient volcanic rock stand out against the lighter terrain. For a few weeks around opposition, Mars rewards attention in a way that it simply doesn't at most other times. Then Earth continues to pull ahead. Mars falls behind. The distance grows. The apparent size of the planet in the sky shrinks. Within a few months, it starts to look like just another point of light. Now think about what sits at the opposite end of the cycle. If opposition is the moment of closest approach, conjunction is the moment of maximum separation. At conjunction, Mars is on the far side of the Sun from Earth. The Sun sits directly between us. Mars is as far from Earth as it can possibly get, roughly 250 million miles. And it is completely invisible. Not dim, not hard to find. Gone. Lost in the glare of the Sun, impossible to observe with any ground-based instrument. You could point your telescope at where Mars should be and see nothing but the blinding light of the Sun drowning everything out. 250 million miles. Think about that for a second. At opposition in 2003, Mars came within 34.8 million miles of Earth. At conjunction, that same planet sits more than 7 times farther away. The ratio is staggering. It means the Mars you see blazing orange in an opposition sky and the Mars sitting invisibly behind the Sun during conjunction are the same world, separated by a difference in distance so enormous that it would take our fastest spacecraft years to cross the gap between those two positions alone. The practical consequences of conjunction go beyond lost observing time. During solar conjunction, mission controllers on Earth lose reliable contact with rovers on the Martian surface. The Sun itself becomes an obstacle. Radio signals traveling between Earth and Mars have to pass through or near the solar corona, the outermost layer of the Sun's atmosphere, and that plasma is electrically active, chaotic, capable of degrading or outright scrambling radio transmissions. NASA has a formal procedure for this. It's called the Mars Solar Conjunction Period. For roughly 2 weeks around every conjunction, mission teams suspend most commanding of rovers and orbiters. They send limited low-risk instructions. They wait. The rovers on the surface operate on preloaded sequences, executing tasks already uploaded before the blackout began. During those 2 weeks, if something goes wrong, Earth cannot respond in real time. The rovers are on their own. That's what conjunction means at our current level of Mars exploration, with robots. Extend that picture to a human crew on the Martian surface during conjunction, dealing with a system failure. and waiting over 40 minutes for a round-trip signal just to ask for help, assuming the signal even gets through. The distance between Earth and Mars doesn't just affect how long missions take to get there. It defines what those missions feel like from the inside, moment to moment, depending entirely on where the two planets are in their dance around the Sun. And then, roughly 13 months after opposition, Mars vanishes into the Sun's glare entirely, sitting on the far side of the solar system at 250 million miles, as unreachable as it ever gets. Not all oppositions are equal, and figuring out which ones will bring Mars unusually close requires tracking a cycle within a cycle within a cycle. We established that opposition happens roughly every 26 months, Earth lapping Mars on the inside track and pulling between it and the Sun. But opposition alone doesn't tell you how close Mars actually gets. Because remember, Mars's orbit is noticeably oval. At perihelion, Mars sits about 128 million miles from the Sun. At aphelion, it's about 154 million miles out. That's a 26 million mile difference just in where Mars is relative to the Sun, and it matters enormously. If Earth catches Mars near aphelion, even at opposition, the two planets might be 60 or 70 million miles apart. But if Earth catches Mars near perihelion, its closest point to the Sun, the geometry tightens dramatically. That's what makes a perihelic opposition different from every other kind. A perihelic opposition happens when two things are true at the same time. Earth is passing between Mars and the Sun, and Mars is simultaneously near the bottom of its orbit, hugging closer to the Sun than usual. The result is that the gap between the two planets shrinks to something genuinely remarkable. Both the 2003 opposition and the 2018 opposition were perihelic, or close to it. In 2003, Mars came within 34.8 million miles. In 2018, it came within about 35.8 million miles. Compare that to the 2022 opposition, which brought Mars no closer than 50.6 million miles, or the 2025 opposition, where the gap will be nearly 60 million miles. Same mechanism, very different results. The difference comes down to where Mars sits on its own elliptical track when Earth catches up. Here's the thing most people don't realize. These perihelic oppositions don't happen every 26 months. They cluster together, and then they disappear for over a decade. The interval between perihelic oppositions is roughly 15 to 17 years. Think about what that means. You can go through 6 or 7 ordinary oppositions, Mars getting reasonably close, but nothing exceptional. And then suddenly one alignment arrives where the geometry is nearly perfect. Those are the events that make headlines. Those are the years when telescopes sell out and astronomy clubs fill their parking lots. The 15 to 17-year interval isn't random. It emerges directly from the interplay between Earth's orbital period of 365 days and Mars's orbital period of 687 days, combined with where Mars sits relative to its own perihelion during each successive opposition. The math works out so that after either 15 or 17 years, sometimes one, sometimes the other, Earth and Mars find themselves in nearly the same relative configuration again. A perihelic opposition follows a perihelic opposition follows a perihelic opposition in that irregular but predictable rhythm. Now go one level deeper. Those 15 and 17-year intervals actually add up to a longer pattern. 15 plus 17 plus 15 plus 17 plus 15 equals 79. Every 79 years, Mars oppositions repeat in a configuration that is strikingly similar to what occurred 79 years before. Similar distance, similar time of year, nearly the same geometry. The 1924 opposition was close. The 2003 opposition was close. Both were perihelic. Separated by 79 years, they shared the same basic structure. But 79 years isn't quite precise enough. Small differences accumulate. The real cycle, the one where oppositions repeat with very high accuracy, runs 284 years. That's 79 plus 79 plus 79 plus 15 plus 17 plus 15. If you want to see how it's built from the shorter intervals. What it means practically is this. The opposition of August 28, 2003, when Mars came closer to Earth than it had in nearly 60,000 years, will not be matched again until August 29, 2287. Not 2040, not 2060, 2287. That's 284 years from 2003. No one alive today will see it. No one born in the next 200 years will see it. And here's where it gets stranger. Even 2003 wasn't the theoretical minimum. The absolute closest Mars and Earth could get would require Mars to reach perihelion at the precise moment Earth completes its overtaking pass. That configuration, Mars at perihelion, Earth at aphelion, both aligned with the Sun, would put the two planets within 33.9 million miles of each other. It has never happened in recorded history, not once. The 2003 approach was 34.8 million miles. The true minimum hasn't been reached yet. What makes all of this more remarkable is that the target is slowly moving. Mars's orbit is not static. Right now, Mars is in a long-term period of increasing orbital eccentricity. Its orbit is gradually becoming more oval. About 19,000 years ago, the eccentricity sat at roughly 0.079. Today, it's 0.0935. In about 24,000 years from now, it will peak at around 0.105. As the orbit stretches, the difference between perihelion and aphelion grows. Perihelic oppositions will bring Mars fractionally closer than they do today. The very closest approaches, the ones that would break the 2003 record, are still ahead of us, not behind. Over millions of years, the eccentricity swings between near circular at around 0.002 and significantly elongated at around 0.12. These changes are driven by gravitational nudges from Jupiter, Saturn, and the other planets. A slow, relentless reshaping of the solar system's geometry across timescales almost too large to hold in your head. That 284-year repetition is a reminder that the solar system operates on timescales that make human history look like a rounding error. Here's something most people never question. When we say Mars is our nearest neighbor in space, we're wrong about which neighbor we mean. The planet that actually holds that title is Venus. On average, Venus comes closer to Earth than Mars ever does. Think about that for a second. All the mission posters, all the talk about Mars as the next step, all the cultural weight we've placed on the red planet, and it isn't even the closest one. Here's the number that matters. Venus, at its nearest approach to Earth, gets within about 25 million miles, sometimes as close as 24 million miles. That's not an exceptional event the way August 2003 was for Mars. That's a fairly routine occurrence built into the basic geometry of Venus's orbit. Compare that to Mars at its all-time record closest approach, 34.8 million miles in 2003, a distance we won't see again until 2287. Even at its absolute historical best, Mars was still roughly 10 million miles farther away than Venus typically gets. And on average, the difference is not even close. Mars averages 140 million miles from Earth. Venus averages something far more modest, a fraction of that. The reason Venus is so consistently nearby comes down to the shape of its orbit. Venus has an orbital eccentricity of just 0.007. To put that in perspective, a perfect circle has an eccentricity of 0, and Venus is almost exactly that. Its orbit is very nearly a perfect ring around the Sun. That means Venus doesn't swing wildly between close and distant the way Mars does. It stays on a reliable, nearly circular path, and the result is that its distance from Earth is relatively predictable and consistently smaller than Mars's. Mars, as we've been covering, is the opposite. Its eccentricity of 0.0935 creates the enormous swings we've been tracking, 34.8 million miles at its closest, over 250 million miles at conjunction. Venus doesn't behave that way. It sits in its nearly circular lane and maintains what is, by planetary standards, a remarkably steady distance. Now, here's where it gets even stranger. If you've absorbed the logic so far, that average distance is what really matters, and that consistent proximity beats occasional record-breaking closeness, then you might expect Venus to be the clear winner. And it is. But some mathematicians and physicists have taken this line of thinking one step further and pointed out something genuinely counterintuitive. Mercury, on average, may actually be the closest planet to Earth. The reasoning works like this. Mercury orbits the Sun quickly, completing a full orbit every 88 days. It never gets to the far side of the solar system relative to Earth, the way Mars does during conjunction. Mars, as we discussed, can sit 250 million miles away when it's on the opposite side of the Sun. Venus can also get fairly distant when it's on the far side of its orbit. Mercury, because of its small, fast orbit, stays relatively close to the Sun at all times, which means from Earth's perspective it's never as catastrophically far as Mars gets. When you calculate the time average distance between each planet and Earth across an entire orbit, Mercury edges out Venus for the top spot. This finding, which appeared in a 2019 paper in Physics Today, surprised a lot of people. Most people have never heard it. But back to the question most people actually care about. If Venus is closer, if Venus is more consistently accessible, why is Mars the destination everyone talks about? Why does Mars appear on the mission posters? Why do we call Mars the obvious next step in human space exploration rather than Venus? The answer is not about distance, it's about conditions. Venus is, in practical terms, one of the least hospitable places in the solar system. Its surface temperature averages around 900 degrees Fahrenheit, hotter than Mercury despite being farther from the Sun. The reason is a runaway greenhouse effect that has turned Venus's atmosphere into a dense, crushing blanket of carbon dioxide and sulfuric acid clouds. The atmospheric pressure at the surface is about 90 times that of Earth's, equivalent to being nearly a mile underwater. Every Soviet lander we sent to Venus in the 1970s and 1980s was destroyed within about 2 hours of arriving. The surface melts lead. Any mission to the Venusian surface with current or near-future technology would be extraordinarily short-lived. Mars, by contrast, is cold and dry and thin-aired and covered in radiation, but it's survivable, at least in theory. You can build a habitat on Mars. You can walk on its surface in a suit. Its day is almost exactly as long as Earth's. It has water ice. It has a carbon dioxide atmosphere that could, in principle, be used for fuel production. The challenges are enormous, but they are the kind of challenges engineering can work on. Venus's challenges are, at this moment, largely unsolvable for a crewed surface mission. So the reason Mars captures the imagination isn't because it's closer, it's because it's the one that seems livable, or at least survivable. Venus may be geographically nearer. It wins that argument clearly on the numbers. But it is a place we cannot go, not yet. Not the way we mean when we talk about sending humans somewhere. Venus is closer on average by a wide margin, but somehow it's Mars that fills our imagination. Mars that appears on mission posters. Mars that we call the obvious next step. The number that actually matters for space missions isn't the 34.8 million miles from 2003. The record that gets quoted in articles, it's the average distance of 140 million miles. That's the number space agencies actually build around. That's the number that shapes timelines, fuel budgets, crew durations, and launch dates. The record-setting close approach of 2003 was a once-in-60,000 years event. You can't plan a space program around a 60,000-year anomaly. You plan around the average. And the average, 140 million miles, tells a very different story than the headline number most people remember. Here's how to put that in context. The distance from Earth to the Sun, what astronomers call one astronomical unit, is about 93 million miles. Mars, at its average distance, is roughly 1.5 times that. So when you picture the Sun out there in space, you picture how far Earth sits from it. Mars is half again as far beyond that. Think about that for a second. The Sun is already incomprehensibly far away. Mars is farther still. If you shrink the Sun down to the size of a bowling ball and place it on the ground in front of you, Earth would sit about 26 feet away. At that same scale, Mars wouldn't be right beside Earth. Depending on where both planets happen to be in their orbits, Mars would be somewhere between 40 feet and roughly 200 feet away. At its closest, it's in the next room. At its farthest, it's halfway down the block. That's the range you're working with, not a fixed point, but a moving target that swings across more than 150 feet of scaled space. And here's the thing most people don't realize. You don't get to pick where Mars is when you decide to go. The planets don't wait for you. They move on their own schedule, governed entirely by orbital mechanics. The window in which a launch is actually practical opens roughly every 26 months and stays open for only a matter of weeks. That window exists because there are specific moments when Earth and Mars are aligned in a way that minimizes the distance the spacecraft needs to travel and, critically, minimizes how much fuel it burns getting there. Outside that window, the geometry works against you. You'd need vastly more fuel to cover what becomes a much longer path. Even then, the travel time stretches well beyond what's practical. Space agencies treat these windows the way a sailor treats the tide. You don't fight it. You plan around it. You prepare for it. And when it opens, you go. The 2020 launch window made this more visible than almost any other moment in the history of Mars exploration. 3 separate countries launched 3 separate missions within 11 days of each other. The United Arab Emirates launched their Hope orbiter on July 19th. China followed with Tianwen-1 on July 23rd. NASA launched the Perseverance rover on July 30th. 3 different space agencies, 3 different spacecraft, 3 different scientific objectives, all departing within the same narrow corridor, because the orbital alignment made that window the optimal one. That is not a coincidence. That is orbital mechanics telling everyone at the same time that now is the moment. If any one of those missions had missed that window, they would have waited. Not weeks, not a few months. 2 years. The next window would have opened in late 2022. By then, the budget cycles, the crew preparation schedules, the hardware storage costs, all of it compounds. Missing a launch window isn't like missing a train where the next one comes in an hour. It's a 2-year delay with financial and logistical consequences that ripple through an entire program. What this means practically is that the accessibility of Mars is not a question of whether you have the rocket ready. It's a question of whether the solar system is cooperating. You can have the most capable launch vehicle ever built sitting on the pad, fully fueled, crew aboard. If the orbital geometry isn't right, you're not going anywhere useful. The planets don't care about your schedule, they have their own. Now, even during a favorable window, the average distance being 140 million miles means the trip itself takes the better part of a year for an unpiloted spacecraft using efficient trajectories. The path isn't a straight line, it's a long curving arc that follows the spacecraft looping around the Sun, gradually catching up with Mars at the other end. This approach, known as a Hohmann transfer orbit, is the fuel-efficient option. A more direct approach would be faster, but the fuel cost escalates dramatically. For robotic missions carrying scientific instruments, the fuel-efficient option is almost always the right call. For human missions, the calculus gets more complicated. This was because you have to weigh fuel cost against the physical toll of a longer journey on a living crew. Either way, the average distance is the reason the journey takes as long as it does. What the 140 million mile average really reveals is that Mars operates on its own timetable. Anyone serious about going there has to accept that from the beginning. You don't decide to go to Mars the way you decide to take a long road trip. You decide years in advance. You plan around a window that opens briefly every 26 months. You build every aspect of the mission around the reality that the distance will be somewhere between close and very far, depending on what the orbits are doing that year. The 2003 record was a gift. Most departures don't get that gift. They get something closer to the average, 140 million miles, a 7 to 9 month transit. A launch window that closes whether you're ready or not. Miss the launch window. You wait another 26 months while the planets realign, which is not how most people picture the process of deciding to go to Mars. Light travels at 186,000 miles per second, the fastest anything in the universe can move, and even at that speed, the distance to Mars introduces a delay that changes everything about how we operate missions there. Think about what that actually means. A radio signal moving at the speed of light takes somewhere between 3 minutes and 22 minutes to reach Mars, depending on where the two planets happen to be in their orbits at that moment. At closest approach, you're looking at roughly 3 minutes one way. At average distance, 140 million miles, that climbs to about 12 or 13 minutes. And at conjunction, when Mars is sitting on the far side of the Sun at 250 million miles, a signal takes over 22 minutes just to arrive. A round-trip exchange, your question, then their answer, takes 44 minutes at minimum, often much longer. There's no version of this problem where someone on Earth picks up a phone and talks to someone on Mars in real time. Physics doesn't allow it. The distance forbids it. And here's the thing most people don't realize. We already live with this limitation every single day that we operate a rover on the Martian surface, and the consequences are significant. When Perseverance needs to cross a stretch of unfamiliar terrain, mission controllers on Earth can't steer it the way you drive a remote control car. They can't watch it hit a rock and swerve. By the time any image of that rock travels 140 million miles back to Earth, Perseverance has already been sitting next to it for 12 minutes. Any correction sent from Earth arrives another 12 minutes after that. So the rover navigates autonomously, using onboard hazard detection to make decisions that no human on Earth is fast enough to make for it. The rover is, in a very real sense, alone out there. It has to be. Now consider what that means when something goes wrong. In 2018, a global dust storm enveloped Mars and began cutting the power supply to the Opportunity rover. Opportunity ran on solar panels, And as the storm thickened, the available sunlight dropped. Engineers on Earth watched the telemetry, sent commands, tried everything they could. But every command took more than 13 minutes to arrive, and every response, if one came at all, took another 13 minutes to return. The storm worsened. Opportunity's last transmission arrived on June 10, 2018. NASA sent recovery commands for months afterward, broadcasting into the silence. The rover never responded. Whether any of those signals arrived in time to matter, whether any of them arrived while Opportunity still had power, is something no one on Earth knew while it was happening. They found out minutes after the fact, every single time. The distance made real-time intervention impossible. The storm made intervention irrelevant. And all Earth could do was listen. That's an uncrewed rover. Now extend that same delay to a human crew. A crew on the Martian surface dealing with a medical emergency sends a message to Earth. They describe the symptoms, the vitals, the situation. That message takes 13 minutes to arrive. Flight surgeons on Earth assess what they're hearing, confer, prepare a response. That response takes another 13 minutes to reach Mars. 26 minutes have passed. In a medical crisis, 26 minutes can be the difference between recoverable and not, and that's at average distance. Near conjunction, you're waiting 44 minutes for a round trip. The crew isn't consulting with Earth, they're informing Earth what they've already decided to do because they have no other option. Earth becomes an observer, not a controller. The autonomy that mission planners design into rover software has to be built instead into the people. There's another layer here that goes even further than the delay. During Mars solar conjunction, the period when Mars passes behind the Sun from Earth's perspective, the Sun's plasma interferes with radio signals passing through it. The signal degrades, it becomes unreliable, it can fail entirely. NASA doesn't attempt to send commands to Mars rovers during solar conjunction. The blackout lasts roughly 2 weeks. During that window, missions are suspended. Rovers are given pre-planned instructions to execute on their own. They go offline from Earth's perspective, not because anything is wrong with the spacecraft, but because the distance and geometry of the solar system make communication impossible. 2 weeks of silence. For a robotic mission, that's a manageable inconvenience. For a human crew, it means 2 weeks with no connection to Earth at all. 2 weeks during which any emergency is entirely theirs to solve. No guidance, no expertise beyond what's on the spacecraft. No voice from home. What's striking about all of this is that it's not a failure of technology. We have extraordinarily capable communication systems. The Deep Space Network, a system of massive radio antennas positioned around Earth, can maintain contact with spacecraft billions of miles away. The problem isn't the hardware. The problem is that 140 million miles divided by the speed of light equals 12 minutes, and no engineering advancement changes that. You cannot build a faster radio signal. You cannot route a message around the delay. The gap is baked into the physics of the distance itself, and it means that human Mars missions will require a fundamental rethinking of how authority, decision-making, and autonomy work in a space crew. Everything we've learned from the ISS, where a crew member can call Earth and get an answer in half a second, becomes obsolete. The crew on Mars is not a remote outpost with Earth as headquarters. They are, practically speaking, on their own. That gap, that long silence between sending a message and getting a response, is not a technical problem waiting to be solved. It's a fundamental consequence of the distance, and for a human crew on Mars, it would be one of the most psychologically isolating realities they'd face. The fastest spacecraft we've sent to Mars took about 7 months to get there. And those spacecraft didn't have to slow down, didn't have to enter orbit, definitely didn't have to come home. That distinction matters more than most people realize. When NASA's Curiosity rover made the journey in 2012, it took about 8.5 months to reach the Martian surface. Perseverance, which landed in 2021, made the trip in roughly 7 months. Both of those missions used what's called a Hohmann transfer orbit, a curved, arcing path that loops partway around the Sun before arriving at Mars. It's not the shortest possible route. It's the most fuel-efficient one. And fuel efficiency, when you're launching from Earth's surface, is essentially everything. Here's the thing most people don't realize about those travel times. The rovers didn't need to carry fuel to slow themselves down into orbit around Mars. They used heat shields, parachutes. In Curiosity's case, the now famous sky crane system, to bleed off velocity at the destination. They also didn't carry fuel for a return trip. They didn't carry food, water, or life support for a crew. They were essentially fuel-light projectiles aimed at a moving target 140 million miles away. A human mission is something entirely different. When you send people, you have to stop. You can't just slam into the Martian atmosphere and call it a landing, at least not at the speeds involved in interplanetary transit. A crewed spacecraft needs to fire its engines against its direction of travel to slow down and enter Mars orbit. That burn requires fuel. Substantial fuel. The mass you have to carry just to decelerate at Mars is significant enough on its own, but then you also need fuel to launch off the Martian surface when it's time to come home. Fuel to do a course correction on the return trip. Fuel to slow down enough to re-enter Earth's atmosphere safely. The Hohmann transfer orbit that works so elegantly for a robotic probe becomes vastly more complicated when you add all of that to the equation. So how long would a human mission actually take? The outbound trip, even using optimized trajectories, would still run between 6 and 9 months depending on the specific launch window and the propulsion system available. That's not a worst-case estimate. That's the range for realistic near-term crewed missions using chemical propulsion, the same basic technology we've relied on since the Apollo era. Some mission architectures propose what's called a conjunction-class mission, where the crew takes a slower trajectory out, waits on Mars for the orbital alignment to return to favorable, then takes another 6 to 9 month journey home. Think about that for a second. 6 to 9 months out, a long stay on the surface, then 6 to 9 months back. The time in transit alone is over a year. There are faster options, at least in theory. Nuclear thermal propulsion, an engine that heats propellant using a nuclear reactor rather than chemical combustion, could potentially cut the transit time to somewhere between 3 and 4 months each way. The specific impulse, which is a measure of how efficiently an engine uses its propellant, is roughly twice as good for nuclear thermal as it is for the best chemical rockets. NASA studied this seriously in the 1960s under Project Nerva. The concept has been revisited multiple times since. A 3 to 4 month trip would meaningfully reduce the radiation exposure crew members accumulate in transit. It would reduce the psychological toll of being locked in a small spacecraft for the better part of a year. But nuclear thermal propulsion remains developmental. We haven't flown one. The engineering, the regulatory challenges, the sheer cost of developing and qualifying such a system mean it's not available for the first human Mars missions, even under optimistic projections. Ion drives are another option worth understanding. They work by ionizing a gas and accelerating the resulting particles to very high velocities, generating thrust. The thrust is extremely low, nothing like a chemical rocket. But ion engines are extraordinarily efficient and can run continuously for months or years. Spacecraft like Dawn and Deep Space One proved the technology works in deep space. The problem is the power requirement. To run an ion drive capable of pushing a crewed Mars spacecraft, something orders of magnitude heavier than Dawn, you'd need power levels that essentially require a nuclear reactor. And even then, the acceleration is so gradual that the transit time doesn't drop as dramatically as you might hope. Ion propulsion makes more sense for cargo missions, pre-positioning supplies at Mars before humans depart. Now, here's where the total mission duration really becomes something you have to sit with. Let's say a crew departs for Mars during a favorable launch window. They spend 7 months in transit. They arrive, begin their work, and almost immediately face a hard reality. The next favorable window to return to Earth doesn't open for roughly 18 to 26 months. The orbital mechanics don't care about the crew's preferences. Earth and Mars have to be in the right positions relative to each other for a return trip to be fuel efficient enough to be survivable, and that alignment only comes around every 26 months. If the crew misses it or arrives too late in the window to prepare a return vehicle, they wait. Not days, not weeks. A year and a half at minimum, potentially longer. The 26-month cycle isn't arbitrary. It's determined by the orbital mechanics of a heliocentric transfer, where both planets must be positioned to allow for a fuel-efficient path between them. Missing a launch window by even a few days can push a mission back by 26 months or more. This constraint shapes every aspect of mission planning. Crew training, equipment maintenance, supply preparation, everything must align with these windows. Mission planners spend years developing launch calendars and contingency timelines before any crewed spacecraft leaves Earth's orbit. The margin for error is remarkably small, and the consequences of missing a window extend far beyond the launch schedule itself. Some mission architectures accept this reality from the beginning. They're designed around a long surface stay, perhaps 500 days on Mars, specifically because that's how long the crew needs to wait for the return window. The alternative is an opposition-class mission, where the crew takes a fast trajectory to Mars, spends only a short time on the surface, sometimes as little as 30 days, and returns on an equally fast trajectory. The trade-off is that opposition-class trajectories require far more fuel and expose the crew to Venus's vicinity during part of the journey. That adds to radiation concerns. They're faster overall, perhaps 1.5 years round trip, but harder to execute. Add it all up under the most realistic near-term scenario. 7 to 9 months out, 18 months or more on the Martian surface waiting for the return window. 7 to 9 months back, 2.5 to 3 years. That's the baseline for a round trip to Mars under the best realistic conditions. It assumes nothing goes wrong. The 26-month launch window isn't a scheduling preference. It's a hard constraint imposed by orbital mechanics, and it shapes everything about how a human Mars mission would actually work. We've already established that the journey to Mars takes roughly 7 to 9 months under current technology. But that number assumes you're leaving at the right moment. The Hohmann transfer orbit, the fuel-efficient curved path that loops a spacecraft around the Sun and intercepts Mars at the other end, only works when Earth and Mars are aligned in a very specific geometry. That alignment opens a window of a few weeks, roughly every 26 months, and then it closes. Miss it, and you're not going to Mars a little late. You're not going for 2 more years. Think about what that means in practical terms. You've spent years training a crew. You've assembled a spacecraft at enormous cost. Engineers have worked around the clock. And then a technical problem, a failed component, a budget shortfall, a health issue with a crew member, forces a delay past the window. Everything stops. The crew disperses. Systems that have been powered up and checked go back into storage. The mission clock resets by 26 months. This has already happened with robotic missions. The Mars Science Laboratory, the mission that delivered Curiosity to the surface, faced serious development pressure, partly because missing a launch window would have meant a 2-year delay and hundreds of millions of dollars in additional costs. For a human mission, those stakes multiply dramatically. Now, the Hohmann transfer isn't the only option. There are faster trajectories that sacrifice fuel efficiency for speed. A high-energy direct trajectory can shorten the transit time, but it requires substantially more propellant, which means a heavier spacecraft at departure, which feeds back into the fuel problem we'll get to in the next section. There are also slower trajectories that take advantage of gravitational assist from other bodies, stretching transit times well beyond 9 months in exchange for fuel savings. Every option involves a different trade-off, and none of them escape the fundamental constraint that the window itself exists only for a limited time. One trajectory type worth understanding specifically is the free return trajectory. Here's the concept. The spacecraft follows a path that, if the engine is never fired again after the initial burn, will naturally loop around Mars and return to Earth. It's a built-in safety net. If something catastrophic happens on the way out, a medical emergency, a critical system failure, the crew doesn't have to burn fuel to turn around. Physics brings them home. The trade-off is that free return trajectories take longer, and they commit the crew to a fixed path from the moment of departure. The moment you fire the engine to insert into Mars orbit, you've left the free return path. You're committed. There is no Apollo 13-style abort from low Mars orbit. The burn that captures you around Mars is also the moment the free return safety net disappears entirely. Here's the thing most people don't realize about what commitment to Mars orbit actually means. Once you're there, the orbital mechanics don't care about emergencies. The return window back to Earth opens on its own schedule, governed by the same 26-month cycle. A crew in Mars orbit or on the Martian surface cannot simply decide to come home. They have to wait for Earth and Mars to reach the correct alignment for a return transfer. That alignment won't arrive for somewhere between 14 and 26 months after arrival, depending on the specific mission profile and when during the synodic cycle the crew arrived. In many serious mission architectures, the crew lands on Mars, conducts their surface operations, and then waits. Not days, not weeks. In some scenarios, they're waiting more than 500 days on the surface before the return window opens. That number isn't a worst-case estimate buried in a footnote. It shows up repeatedly in mission planning documents as an expected feature of the mission profile. The crew would live on Mars for longer than they spent traveling to get there. They'd watch the return window approach on a calendar they've been counting down since before they even left Earth. What that 500-day wait actually requires is staggering. Enough food, water recycling capacity, power generation, and habitat integrity to support a crew for a year and a half on a planet with a toxic atmosphere, punishing radiation levels, and the potential for global dust storms. And all of that infrastructure either has to arrive with the crew or be pre-positioned by robotic missions years in advance. If a critical system fails at day 200 of that surface stay, there is no resupply. There is no repair crew. Mission control on Earth can advise with a 20-minute delay on each end of the conversation, but the crew is on their own. This is categorically different from anything humanity has ever attempted in the history of exploration. Antarctic expeditions are resupplied, submarine surface. The ISS has crew rotation. The Moon is 3 days away. A Mars crew waiting out the return window is genuinely isolated in a way that has no precedent. The distance that makes the launch window so rigid is the same distance that makes early return essentially impossible once the crew has committed to the mission profile. Some proposals get around this by staging the mission in pieces, sending supplies ahead on one launch window, then sending the crew on the next, with pre-positioned resources already waiting on Mars. That helps with the surface stay logistics. It doesn't change the core constraint. The crew still departs in a window measured in weeks. They still commit to a 500-day surface stay once they arrive. They still fly home in a window that opens on Mars's schedule, not theirs. And that waiting period, 500 days on the surface of another planet with no possibility of early return, isn't a detail buried in the mission architecture. It's one of the central facts of what it would mean to go to Mars. The fundamental challenge of getting to Mars isn't really about the distance. It's about the fuel required to cross that distance, and how that requirement compounds on itself in ways that are genuinely brutal. There's an equation that every rocket engineer knows, and it has a nickname: the tyranny of the rocket equation. Here's the basic problem. To move something through space, you need to burn fuel. But fuel has mass, and that mass needs to be accelerated too, which means you need more fuel. And that additional fuel has its own mass, which means you need even more fuel to move the fuel you're carrying to move the fuel you're carrying. The cycle compounds exponentially, not linearly, exponentially. Every kilogram you want to deliver somewhere costs you far more than a kilogram of fuel at launch. This isn't a flaw in our engineering. It's a mathematical reality baked into the physics of spaceflight. Think about what this means for a Mars mission specifically. Curiosity, the car-sized rover currently on the Martian surface, required a rocket the size of a 10-story building just to get off the ground. And Curiosity weighs about 900 kilograms. A crewed spacecraft would need to carry humans, a habitat module, food, water, life support equipment, scientific instruments, and enough fuel to slow down when it arrives at Mars. We're talking about something that might weigh 100,000 kilograms or more. The fuel requirement for that mission doesn't scale up proportionally. It scales up catastrophically. This is exactly why every Mars mission we've ever sent has been a small robotic vehicle. Not because robots are smarter than engineers, and not because we don't want to send humans. It's because the rocket equation makes sending humans to Mars one of the most logistically punishing undertakings in the history of engineering. The fuel requirement is so extreme that you can't simply build a bigger rocket and call it solved. SpaceX has been trying to address this with Starship, which is currently the most credible architecture for a crewed Mars mission. The plan isn't to launch the full mission from Earth's surface in a single attempt. It can't be done that way. The fuel load is too large to get off the ground. Instead, Starship would launch into Earth orbit essentially empty of propellant, and multiple tanker spacecraft would then be sent up separately to refuel it in orbit. Multiple launches just to fill the tank. Only then, once Starship is fully fueled in orbit, would it fire its engines and head for Mars. That's how severe the rocket equation problem is. We can't even launch the fuel from the ground. We have to assemble the fuel supply in orbit first. Think about that for a second. The logistics of refueling in orbit require a series of precision rendezvous and docking operations, with each tanker carrying liquid methane and liquid oxygen, all of which has to be transferred to the waiting spacecraft without significant losses from boil-off. Cryogenic propellants don't sit patiently in a tank in the vacuum of space. They evaporate. Slowly, but they evaporate. And every kilogram lost to boil-off is a kilogram that doesn't reach Mars. The orbital refueling problem alone has consumed years of engineering effort. Now here's where the problem gets even more complex. Getting to Mars is only half of it. The crew has to come home. That means the return propellant has to come from somewhere. If you launch it from Earth, you've just doubled your fuel problem. Every kilogram of return fuel adds to the mass you have to deliver to Mars, which adds to the fuel required to get there in the first place, which feeds right back into the rocket equation spiral. The proposed solution is something called in situ resource utilization, ISRU. The idea is to make the return fuel on Mars itself using materials already present on the surface. Mars has an atmosphere that's about 95% carbon dioxide. If you bring hydrogen from Earth or extract water ice from the Martian soil, you can run a chemical reaction, the Sabatier reaction, that combines carbon dioxide and hydrogen to produce methane and water. Methane is a rocket propellant. Liquid methane specifically is exactly what Starship is designed to burn. In theory, a propellant production plant on the Martian surface could manufacture enough fuel to launch the crew back to Earth without any of that fuel having to make the outbound trip. This is not science fiction. NASA had been testing the basic concept on Mars right now. The MOXIE experiment, the Mars Oxygen In Situ Resource Utilization Experiment, flew to Mars aboard the Perseverance rover and has been extracting oxygen from the Martian atmosphere by breaking apart carbon dioxide molecules. It's worked. In tests conducted between 2021 and 2023, MOXIE produced oxygen at the rate expected and demonstrated that the chemistry functions in the actual Martian environment. At full scale, the same process could supply both the oxidizer for rocket propellant and breathable oxygen for a crew. But here's the thing most people don't realize. ISRU at the scale needed for a crewed return mission requires serious industrial infrastructure on Mars before humans arrive. We're talking about a propellant plant, power systems to run it, probably nuclear, storage tanks, and enough lead time to fill those tanks before the crew lands. That infrastructure has to get to Mars somehow, which means robotic precursor missions, which need their own launch windows, their own fuel, their own years of transit time. The crew can't land and then wait for their return fuel to be manufactured. They need it waiting for them. The chicken and egg nature of this problem is real. You can't colonize Mars without fuel produced on Mars. You can't produce fuel on Mars without infrastructure. You can't deliver infrastructure without solving the same rocket equation problem that makes colonization hard in the first place. Every solution opens into another layer of the same fundamental constraint. Every kilogram of payload you want to land on Mars requires several kilograms of fuel, which requires its own fuel to accelerate, and the math spirals outward in a way that makes the distance feel almost secondary to the engineering problem it creates. The spacecraft that carries humans to Mars would need to be a completely self-contained world, not because it would be elegant or comfortable, but because there is no alternative. Think about what that actually means. Every breath the crew takes, every sip of water, every calorie of food, all of it has to come from systems the spacecraft carries or generates internally for 9 months, with no resupply and no outside help. The International Space Station runs closed-loop life support too, but the ISS gets cargo deliveries. A Mars-bound crew does not. If something runs out, it runs out. If something breaks, the crew fixes it themselves or they die. That's the operating reality from the moment the spacecraft leaves Earth orbit. Water is the first place this gets genuinely difficult. The human body loses water constantly through breathing, sweating, and other biological processes. On a 9-month journey with a crew of 4 to 6 people, that adds up fast. You can't carry enough fresh water to replace what's lost, so the system has to recycle it. Not mostly, essentially all of it. We're talking about recycling humidity from the air, urine, everything. The ISS already does this, and its water recovery system operates at roughly 90 to 93% efficiency. That sounds high, but the remaining 6 or 7% that's lost adds up over 9 months in a way that becomes a serious problem. A Mars mission needs to push that efficiency closer to 98 or 99%. And that system needs to run without failure, without spare parts being flown up, for the entire duration of the transit. Carbon dioxide is the next problem. Humans exhale it continuously. In a sealed spacecraft, CO2 builds up rapidly unless it's actively scrubbed from the air. Current ISS systems handle this, but they rely on periodic resupply of chemical scrubbing materials. A Mars spacecraft needs a regenerative system, one that captures the CO2, processes it, and either releases oxygen back into the cabin or stores the carbon for other uses. The engineering exists in prototype form. Making it reliable enough to run without maintenance for 9 months is a different challenge entirely. Thermal control is equally unforgiving. A spacecraft in space loses heat through radiation and gains heat from the sun depending on orientation and solar exposure. Overheating could disable critical electronics or make the cabin uninhabitable. Overcooling wastes power and creates crew discomfort. The thermal management system has to maintain precise temperature ranges across the entire vehicle while managing the heat generated by life support equipment, computers, and human metabolism. Like the other systems, it needs redundancy, multiple radiators, backup temperature regulation, independent monitoring. A thermal failure that leads to uncontrolled heating or cooling doesn't give the crew much time to respond. Now consider food. A crew of 6 people over 9 months. Conservative estimates put the food mass requirement at somewhere between 1 and 2 metric tons, depending on calorie density and packaging. That's before you account for the packaging itself, which adds significant mass. Here's the thing most people don't realize. Food mass is not just a supply problem, it's a fuel problem. Every additional kilogram on that spacecraft requires more propellant to accelerate it. So mission architects face a brutal trade-off. Dense, pre-packaged rations reduce mass, but create crew morale and nutrition problems over long durations. Some proposals incorporate small-scale hydroponic growing, fresh vegetables, psychological benefits, some oxygen production. But growing food in microgravity requires space, power, water, and introduces biological complexity into an already complex system. There's no clean answer. Then there's what 9 months of microgravity does to the human body. This is not a minor concern. It's one of the most serious medical challenges of the entire mission. Bone density loss in microgravity runs at roughly 1 to 2% per month in load-bearing bones. Muscle mass drops. Fluid shifts toward the head, increasing intracranial pressure in ways that have been linked to measurable vision deterioration in long-duration astronauts. The immune system weakens. Cardiovascular deconditioning sets in. Astronauts on the ISS exercise 2 hours every single day specifically to slow these effects, and they still arrive back on Earth after 6 months, needing weeks of rehabilitation. A Mars crew would need to arrive not just alive, but healthy enough to immediately begin surface operations in Mars's gravity. They can't spend 2 weeks recovering. There's too much to do. The theoretical solution is artificial gravity, spinning the spacecraft or a section of it to create centrifugal force that mimics gravity. It works in principle. The engineering to implement it adds enormous mass and structural complexity. You need a rotating section large enough that the rotation rate doesn't cause debilitating motion sickness, which means a large radius, which means a large and heavy structure. No crewed spacecraft has ever used this approach. It remains theoretically sound and practically unbuilt. So crews would almost certainly make the transit in microgravity, exercising heavily, accepting some level of physiological degradation, and arriving at Mars in a compromised state. Mission medical plans account for this. Whether those plans are adequate is something we won't fully know until people actually make the trip. And underneath all of this sits the question of what happens when something breaks. Not if, when. In 9 months of continuous operation, systems fail. Pumps seize, filters clog, sensors give false readings. On the ISS, ground teams and supply missions backstop every system failure. On a Mars transit vehicle, the crew is on their own. Every critical system needs redundancy. The water recycler needs a backup. The CO2 scrubber needs a backup. The oxygen generation system needs a backup. Power systems need redundancy, and the backups themselves need to work because there's no third option. This drives spacecraft mass upward and engineering complexity upward, which drives cost upward, which drives the political difficulty of actually building and launching the mission upward. A single point of failure in life support is not an emergency with solutions. It's a crew-ending event. That's the design requirement the engineers work backward from. Every component of the life support system has to be treated as if the mission ends the moment it fails without a backup. That mentality drives decisions about materials, maintenance schedules, crew training, and the sheer volume of spare parts the spacecraft has to carry. Keeping 4 to 6 people alive and functional for 9 months in interplanetary space with no resupply and no rescue requires every system to work, every single day without exception for the entire duration. Of all the dangers facing a human crew on the way to Mars, radiation is the one that works on you quietly, invisibly, every single hour of the journey. Every other threat on a Mars mission has a moment of crisis, a system failure, a warning alarm, a number that goes wrong on a display. Radiation doesn't announce itself. You don't feel it accumulating. It builds silently in the cells of your body across months of transit and months on the surface. The consequences show up years or decades after you've returned. That is what makes it so difficult to communicate and so easy to underestimate. Here's the thing most people don't realize. On Earth, you are protected by 2 overlapping shields. The first is the planet's magnetic field, a vast bubble of magnetism generated by the churning iron in Earth's core, extending tens of thousands of miles into space. It deflects charged particles streaming from the sun and from deep space. The second is the atmosphere, a column of air roughly equivalent to 10 meters of water sitting above your head at all times, absorbing and scattering radiation before it reaches the surface. You have never spent a single day of your life without both of those shields in place. In interplanetary space between Earth and Mars, you have neither. Think about that for a second. Not reduced protection, not partial protection. None. The radiation environment in interplanetary space comes in 2 distinct forms. Each is dangerous in its own way. The first is galactic cosmic rays, a constant low-level background of extremely high-energy particles originating from outside the solar system. These aren't the relatively gentle particles emitted by the sun. Galactic cosmic rays are the remnants of distant supernovae, accelerated to enormous energies over millions of years. They pass through spacecraft walls. They pass through the human body. Dense shielding helps, but high-energy cosmic rays interact with the shielding material itself, producing secondary particles, sometimes making the problem worse rather than better depending on what you use. There is no practical way to stop them entirely. The second type is solar energetic particle events, sudden bursts of radiation from solar flares and coronal mass ejections. These events can deliver a dangerous dose in a matter of hours. We can predict them somewhat because modern solar monitoring gives some advance warning, but not always enough. A major solar particle event reaching an unshielded crew could be lethal, and predicting exactly when one will occur, precisely how large it will be. Whether the warning systems will catch it in time is not a guarantee anyone can make. We know what these numbers look like in practice because we've actually measured them. NASA's RAD instrument, the Radiation Assessment Detector, flew to Mars aboard the Curiosity rover, recording the radiation environment during the 8.5-month transit. What it found should be taken seriously by anyone who talks about Mars missions casually. The radiation dose during that journey was equivalent to receiving a full-body CT scan roughly every 5 to 6 days. Not once, not occasionally, every 5 to 6 days for 8.5 months, continuously. By the time Curiosity arrived, the accumulated transit dose alone already exceeded what NASA currently allows astronauts to receive over their entire careers. And that's one way. A round trip plus a surface stay pushes the total dose into territory that mission planners have to address directly and honestly. The shielding options are real but limited. Water is an effective radiation shield. A Mars spacecraft would likely have water storage positioned strategically around crew sleeping areas to provide some protection during the transit. Polyethylene, a hydrogen-rich plastic, absorbs radiation well relative to its mass. Regolith, the Martian soil, could shield a surface habitat if enough of it were piled on top. Each of these options works, up to a point. The problem is mass. Every kilogram of shielding you add to the spacecraft is a kilogram that has to be launched from Earth, accelerated across 140 million miles, and decelerated at Mars. The rocket equation makes mass expensive in a way that compounds brutally, as we've covered. So you shield as much as you can afford to carry. You accept that it won't be enough to eliminate the exposure entirely. The crew would need a dedicated radiation shelter, a smaller, heavily shielded area inside the spacecraft where everyone retreats during a solar energetic particle event. When a CME warning comes in, you abandon whatever you're doing and get inside that shelter. You stay there until the event passes. That shelter needs to be robust enough to reduce the dose to survivable levels during the worst plausible events. Designing it, building it, making sure it can be reached quickly enough when the warning arrives is one of the specific engineering challenges mission planners work through in detail. On Mars itself, the situation is better, but not good. The Martian atmosphere is about 1% of Earth's atmospheric pressure. It provides some shielding. Measurably less radiation reaches the surface than exists in interplanetary space. But 1% of Earth's atmosphere is not a meaningful shield by any measure we'd consider acceptable for long-term human habitation. Surface radiation on Mars is still several times higher than on Earth. Crews on the surface would need to shelter in habitats with additional radiation protection. Surface excursions in spacesuits would continue to accumulate dose. Living underground, in lava tubes or beneath enough regolith, would offer substantially better protection. Some mission architects consider subsurface habitation for exactly that reason. The cancer risk is the long-term consequence that doesn't disappear when the crew lands back on Earth. Mission planners don't pretend otherwise. The calculated increase in lifetime cancer risk for a Mars crew, based on current models, is significant, higher than what most high-risk professions accept, higher than what current astronaut career limits permit. Getting to Mars and back under any realistic scenario means accepting a measurably increased probability of a cancer diagnosis years after the mission ends. That is a known, calculated, pre-accepted consequence built into the mission design, not an unknown risk waiting to be discovered. There is no engineering solution that eliminates the radiation problem, only mitigation strategies that reduce it to a level that mission planners have decided in advance is an acceptable risk for the crew to take. 9 months doesn't sound like a very long time, until you picture spending it in a vehicle roughly the size of a large recreational vehicle with the same 3 to 5 people, unable to leave, unable to go outside, watching the communication delay to Earth grow longer every week. That's the reality of the transit to Mars. And here's the thing most people don't realize. The engineering problems, the radiation, the fuel math. Those are problems you can calculate. You can run the numbers, design a solution, test it. The psychological challenge is different. It doesn't show up cleanly in simulations. It accumulates, it compounds. And by the time you realize how bad it's gotten, you're already 80 million miles from anyone who can help you. Let's start with the communication delay because it changes everything about the psychological experience of the journey. At launch, the delay is already a few minutes each way. By the midpoint of the transit, you're looking at 10 to 15 minutes. By the time the crew approaches Mars, the delay has grown to over 20 minutes each way. Think about that for a second. You send a message to your family on Earth. You wait 40 minutes for a response. There's no phone call, no video chat where someone responds in real time, no way to hear a voice that reacts to what you just said. Every conversation is a letter. Every emotional exchange is delayed by nearly an hour in total. That's not a minor inconvenience. That's a fundamental severance from the world you left behind. News from Earth arrives out of date. Events happen, and the crew finds out about them long after everyone on Earth has already processed them and moved on. The psychological effect of that lag, of feeling perpetually behind, perpetually disconnected, is something researchers studying isolated environments have documented over and over. You're not just far from home. You're out of sync with it in a way that feels deeply disorienting. We actually have data on this. Scientists haven't sent humans to Mars yet, but they've done the next best thing. They've locked people in. The Mars 500 study ran from 2010 to 2011, confining 6 volunteers inside a sealed facility in Moscow for 520 days, simulating the isolation and communication delays of a full Mars mission. What they found was striking. Participants showed measurable deterioration over time. Activity levels dropped significantly. Sleep became disrupted and irregular. Interpersonal tension built up in ways that were sometimes manageable and sometimes weren't. One participant spent large portions of the mission in a state of low-grade psychological withdrawal, and that was on Earth, with the knowledge that they could walk out if something went truly wrong. A Mars crew wouldn't have that option. Antarctic overwintering stations provide another data point. Small groups of people spending 8 to 14 months in extreme isolation in conditions that roughly approximate the confined, monotonous experience of deep space transit. Researchers who study these populations have identified a reliable psychological arc. There's a honeymoon phase early on, novelty, excitement, a sense of shared purpose. Then conflict starts to emerge. Small irritations become large ones. The same faces every day stop being familiar and start feeling suffocating. Eventually, most groups reach some form of acceptance, a psychological settling in. But not always, and not without cost. On a Mars mission, there's no way to send someone home if the conflict phase doesn't resolve. There's no rotation of crew members to break the dynamic. You have 4 to 6 people, and those are the only people available for the entire duration. Every interpersonal problem, every clash of personalities, every grievance that builds over months has to be resolved within that group, or not resolved at all, and simply endured. Now extend the timeline. The 9-month outbound journey is just the beginning. After that comes a surface stay of at least 500 days, potentially longer depending on the mission profile and the return launch window. Then another 9 months back. Total isolation time from departure to landing back on Earth approaches 30 months, 2.5 years. The psychological challenge isn't a sprint. It's an endurance event unlike anything we've tested on human beings. Mission planners know this. They screen for psychological resilience. They look for people with demonstrated histories of functioning well under pressure, in confined spaces, with limited social contact. But here's the uncomfortable truth. You cannot fully simulate what years of interplanetary isolation actually feels like. You can approximate it. You cannot replicate it. The knowledge that you can leave, that someone can reach you in an emergency, that Earth is still functionally accessible, that knowledge changes the psychological experience fundamentally. A Mars crew wouldn't have it. There are scenarios that are almost impossible to train for. What happens if a crew member dies in transit? There's no returning the body to Earth. There's no bringing in a grief counselor. There's no funeral attended by family. The remaining crew members grieve while continuing to perform technically demanding work in the same space where that person lived and died, for months or years before they return home. The psychological weight of that, of carrying loss with no resolution, no ceremony, no community to absorb it, is something we've never asked humans to manage in anything like those circumstances. What the crew would need isn't just training for pressure. They'd need tools for maintaining relationships through sustained stress, protocols for conflict resolution that don't rely on separation or outside arbitration, psychological support from Earth that works with a 20-minute time lag, which means asynchronous therapy sessions, pre-recorded resources, structured communication schedules designed around the delay. Mission planners are working on all of this, but none of it has been tested at the scale and duration that a Mars mission would require. The psychological screening and training for a Mars crew won't just be about selecting people who can handle pressure. It will be about selecting people who can remain functional and cooperative through what may be the most prolonged and inescapable isolation any human has ever voluntarily entered. After 7 or 8 months of travel, Mars grows in the viewports, no longer just a reddish point of light in the star field, but a visible disk, and then a world, and then the place you have to land. That moment, when Mars stops being an abstraction and becomes a destination, is the moment everything gets harder. Because getting to Mars isn't the same as arriving at Mars. The crew has spent the better part of a year in microgravity. Their bones have thinned, their muscles have weakened, their cardiovascular systems have adapted to a reality where the heart doesn't have to fight gravity. And now they need to perform one of the most technically demanding maneuvers in human spaceflight. Not after a rest, not after recovery, right now. The first thing that has to happen is orbital insertion. The spacecraft is traveling tens of thousands of miles per hour relative to Mars. To enter orbit rather than fly straight past the planet, the crew has to fire the main engines in a sustained burn that bleeds off enough velocity for Mars's gravity to capture the vehicle. This burn is not optional. It cannot be skipped or partially completed. If it fails, the spacecraft continues past Mars and out into deep space with no realistic prospect of return. There is no abort option at this stage. Either the engine fires correctly for the full duration, or the mission ends right there. Here's the thing most people don't realize about orbital insertion. It happens behind Mars, out of contact with Earth. The crew is on the other side of the planet when the burn occurs. Mission controllers on Earth can't monitor it in real time. They can't intervene. They can't help. The crew fires the engine, waits, and then either emerges from behind Mars in orbit or doesn't come back at all. Think about that for a second. Once the spacecraft is in orbit, the crew still has to get to the surface. And this is where Mars becomes uniquely unforgiving. Mars has an atmosphere, but barely. It's about 1% of Earth's atmospheric pressure. That's enough to create serious heating problems during entry. It is not enough to slow a large vehicle down the way Earth's atmosphere slows returning spacecraft. You get the friction and the heat without getting the braking effect. For robotic landers, NASA has called the entry, descent, and landing sequence the 7 minutes of terror. The period between atmospheric entry and surface contact when the vehicle is decelerating from over 12,000 miles per hour to zero, using heat shields to survive the initial plunge, parachutes to slow the descent, and retro rockets to handle the final approach. For a human mission, the vehicle is dramatically heavier than any rover we've ever landed. The parachutes that worked for Curiosity and Perseverance aren't scaled to handle that mass. The heat shields have to be larger. The retro rocket systems have to be more powerful. Every element of that 7-minute sequence has to work in exactly the right order at exactly the right time, with no possibility of human intervention from Earth because the signal delay is too long. By the time mission controllers on Earth even know the landing has begun, it's already over, one way or another. The crew lands. Assume everything worked. Now what? They're wearing suits inside a vehicle on the surface of a planet with an unbreathable atmosphere and radiation levels that, while lower than what they experienced in transit, are still several times higher than what you'd encounter on Earth's surface. Before they can do anything, before they can rest, before they can eat a real meal, before they can take off their suits, they need habitat. Pressurized, shielded habitat. And that habitat cannot have arrived with them. The mass required to land a crew safely already pushes the limits of what any rocket can deliver to Mars. You cannot add months of supplies, pressurized living quarters, power generation equipment, and radiation shielding on top of that and expect to land successfully, which means the habitat has to be there before the crew arrives. It has to have been sent ahead on earlier robotic missions, landed autonomously, set up remotely, and verified as operational before any human being gets on the rocket. If something went wrong with the habitat during those robotic missions, if it landed off target, if a system failed, if the pressurization is compromised, the crew lands to find a structure they cannot safely enter. That is not a hypothetical worst case. It is a mission design problem that Eve, our I-Sirius Mars architecture, has to solve before the first crew departs. Assuming the habitat is ready, the crew transfers from the lander, gets the habitat pressurized, and begins a surface stay that is measured not in days, but in months. The length of that stay isn't chosen for comfort or mission objectives. It's dictated by orbital mechanics. The return launch window, the alignment that makes it possible to leave Mars and intercept Earth, opens on its own schedule. Miss it, and the crew waits 26 more months for the next one. Every hour on the surface is an hour spent managing consumables, monitoring systems, and tracking that window. And the moment the crew steps out onto the Martian surface, they're already calculating the return window, because the distance that brought them here is going to determine exactly how long they have before they can leave. Mars is not the welcoming frontier that mission posters tend to suggest. Once you're actually there, after 7 or 8 months of transit, after the bone loss and the radiation and the psychological grind of the journey, you step out onto a surface that the human body was never designed to survive. Not for a minute. Not for a second without a suit between you and the environment. and the environment is not forgiving. Start with the temperature. The average surface temperature on Mars is around negative 80 degrees Fahrenheit. That's negative 62 Celsius. Think about that for a second. That's colder than the coldest recorded temperature ever measured on Earth's surface. And that's the average. At the poles in winter, temperatures drop to around negative 220 degrees Fahrenheit. The atmosphere is so thin that heat doesn't transfer through wind the way it does on Earth, so wind chill is essentially not a factor. But that thinness cuts the other way too. There's almost nothing to hold warmth in. The moment you step into shadow, temperatures plummet. Near the equator on a summer afternoon, you might see temperatures approach 70 degrees Fahrenheit at the surface. But you'd still be standing in an atmosphere you cannot breathe, under radiation levels that are slowly damaging your DNA. The warmth doesn't help you as much as you'd want it to. That atmosphere deserves its own attention. It's approximately 95% carbon dioxide, with nitrogen making up about 3% and argon around 1.6%. There is essentially no oxygen, and even if there were, it wouldn't matter, because the atmospheric pressure on Mars is roughly 0.6% of Earth's. Stand on the surface without a pressurized suit and your blood would begin to boil. The atmospheric pressure is so low that liquid water cannot exist on the open surface. It would either freeze or vaporize immediately. The sky on Mars is a pale butterscotch color from suspended dust particles, and you'd be standing at the bottom of it in a pressure suit, looking out at a desert that stretches in every direction, knowing that the air around you would kill you faster than the cold. Here's where things get even more uncomfortable. Mars has dust storms. Not the kind of dust storm you might picture from a desert on Earth. Global dust storms, events that can envelop the entire planet simultaneously, and they can last for months. In 2018, a global dust storm ended the Opportunity rover's mission. Opportunity had been operating for over 14 years. The storm blotted out enough sunlight that the solar-powered rover couldn't charge its batteries. It went silent. It never woke up. That was a rover. Now picture a human crew during the same event. Solar power generation drops towards zero. Going outside becomes essentially impossible. Visibility is near nothing, and the abrasive dust gets into everything. The crew is confined to the habitat for weeks or months, running on whatever backup power systems were pre-positioned, rationing resources, waiting for the storm to pass. Mission planners know this risk exists. There's no way to eliminate it. Now let's talk about what Mars actually looks like when the sky is clear. Because there's something genuinely extraordinary about this planet, buried beneath all the hostility. Mars has ancient river valleys carved into its surface, channels that could only have been cut by flowing liquid water billions of years ago. It has vast floodplains. It has polar ice caps made of water ice and frozen carbon dioxide. It has the largest volcano in the entire solar system, Olympus Mons, a shield volcano so massive it stands roughly 3 times the height of Mount Everest, and is so wide that if you stood at its base, the summit would be beyond the horizon. You wouldn't even be able to see it from the ground. It has Valles Marineris, a canyon system that stretches roughly the equivalent of the continental United States from coast to coast. The Grand Canyon, by comparison, looks like a scratch. These are real features on a real world, and they tell a story about a planet that was once dramatically different from what it is today. Mars also has 2 moons, Phobos and Deimos. They're tiny, irregular, potato-shaped objects that are almost certainly captured asteroids. Phobos orbits so close to Mars, closer than any other moon to its planet, that it actually orbits faster than Mars rotates. It rises in the west and sets in the east, completing an orbit in under 8 hours. It's also slowly spiraling inward. Within about 50 million years, it will either crash into Mars or break apart into a ring. These aren't moons in the way we think of Earth's moon. They're small enough that from the surface of Mars, Phobos looks roughly 1/3 the size of our moon in Earth's sky. The question of water, and what water might mean, is the one that scientists keep coming back to. All that evidence of ancient riverbeds and floodplains points to a Mars that once had liquid water on its surface, possibly a lot of it, possibly for long enough that something could have developed in it. There's no definitive evidence of past life on Mars. None. And no evidence of current life either. But the question hasn't been closed, and that's exactly why the planet draws the attention it does. The possibility, however remote, that Mars harbored microbial life at some point in its history, or that something might still exist deep underground near liquid water, is not a question science has answered yet. The planet that has captured our imagination for over a century, that we've named rovers after and sent dozens of spacecraft toward, is in reality a cold, thin-aired, radiation-bathed desert that would kill an unprotected human in minutes. And that's before we even get into the dust storms. None of the engineering challenges, the radiation, the isolation, the duration, none of it would be as daunting if Mars were simply closer. But here's the thing. Most people don't sit with long enough. We know all of this. We've known it for decades. The radiation numbers, the travel times, the fuel math. None of it is hidden. And yet the case for going keeps getting made, keeps getting funded, keeps attracting some of the most serious engineers and scientists on the planet. So the question worth asking is, why? What is it about Mars, at 140 million miles on average, costing potentially $1 trillion to reach with humans, that still compels us? The most serious answer is also the most uncomfortable one. Earth is a single point of failure. Everything humanity has ever built, every person who has ever lived, every record of our existence, all of it sits on one planet in one solar system, exposed to asteroids, to supervolcanoes, to pandemics, to the full range of ways a civilization can collapse. A species that lives on one world is a species that can be erased in a single event. Mars, at its closest, is 34.8 million miles away. That distance is a liability for travel, but it's an asset for survival. A catastrophe that ends life on Earth would not automatically reach Mars. Think about that for a second. The historical precedent is sobering. We have examples of civilizations that collapsed when environmental or catastrophic events struck their core regions. The difference now is scale. A sufficiently large asteroid, a supervolcanic eruption with atmospheric consequences, or an engineered biological threat could affect the entire planet simultaneously. Climate change, nuclear conflict, or a truly lethal pandemic with global transmission speed. These aren't science fiction scenarios. They're risks that serious people in risk assessment take seriously. Having a human presence on another world doesn't prevent earthbound catastrophes, but it means that if one occurs, human knowledge, genetics, and culture wouldn't necessarily end with our home planet. It's an uncomfortable form of hope, but it's hope nonetheless. That's the argument behind the long-term vision. Not tourism, not resources, not scientific curiosity. Survival. The idea of a self-sustaining human presence on Mars as insurance for the species. Elon Musk has stated this directly and repeatedly. His goal is not a research outpost or a flags and footprints moment. He's described a self-sustaining city of 1 million people on Mars as the actual target. Not in one mission, not in 1 decade, but as a trajectory, a destination that justifies the cost of everything that comes before it. 1 million people on Mars requires something that goes far beyond sending a crew of 6. It requires infrastructure, energy, food production, manufacturing, medicine, an entire civilization rebuilt from scratch on a world with no breathable air and average temperatures of -80 degrees Fahrenheit. The step beyond that, the one that exists mostly in theoretical discussions for now, is terraforming. The idea that over centuries or millennia you could warm Mars, release its frozen carbon dioxide, thicken its atmosphere, and eventually produce conditions closer to what life on Earth requires. Not comfortable conditions, but survivable ones, without a suit. Here's the thing, though. Terraforming Mars raises a question we haven't fully answered yet. Do we know Mars is dead? We've found no life there, not definitively, not yet, but we haven't ruled it out. If there is microbial life on Mars, even extremophiles buried in subsurface ice or tucked into hydrothermal vents, terraforming would be a planetary extinction event. We would be wiping out an entire biosphere, possibly the only other living system in the solar system, to make the planet more convenient for us. That's not a technical problem, that's an ethical one, and it doesn't have an easy answer. The funding reality is its own kind of sobering. Estimates for a human Mars mission, not a colony just getting boots on the ground once, range from hundreds of billions of dollars to over $1 trillion. That's not a one-time budget line. It requires sustained political will across multiple administrations, across decades, in countries where priorities shift every 4 years. NASA's current realistic projections put a first human landing somewhere in the 2030s at the optimistic end, with the 2040s and 2050s being more honest assessments of what the engineering, budget, and political continuity actually allow. The perception of imminent colonization, the idea that Mars is years, not decades away, is not supported by the trajectory we're actually on. And all of that, the survival argument, the terraforming debate, the funding gaps, the timeline, runs directly through the distance. If Mars averaged 20 million miles instead of 140 million, the launch windows would come more frequently. Travel time would drop from 7 months to weeks. Communication delays would shrink to seconds. The radiation exposure during transit would be a fraction of what it currently is. The entire architecture of a Mars mission changes when you change the distance, and every version of it gets easier. Not easy. Easier. The distance is not incidental to why Mars is hard. The distance is the reason Mars is hard, the thing everything else flows from, the number that sits quietly at the center of every optimistic projection and every sobering calculation alike. We've spent tonight looking at what Mars's distance actually means, not as a number in a textbook, but as a physical reality with consequences for every aspect of getting there. Here's the thing most people walk away with after hearing about Mars. They hear closest planet, and they picture something manageable, something just over the horizon. And that picture is wrong in ways that matter enormously, not just to scientists or engineers, but to anyone who actually wants to understand what it would mean to go there. In cosmic terms, yes, Mars is our backyard. The galaxy is roughly 100,000 light-years across. The nearest star system is 4.24 light-years away. Mars, at its average distance of 140 million miles, is practically on top of us by those standards. But cosmic terms aren't the terms that human bodies operate in. Human lungs and bones and psyches don't experience distance in light-years. They experience it in months of confinement, in communication delays that stretch past 20 minutes each way, in radiation accumulating silently in tissue every single hour of the journey. Think about what we've covered tonight. The closest Mars has ever come to Earth in all of recorded human history was 34.8 million miles. That happened once, in August 2003, and it won't happen again until 2287. You will not see it. Your children will not see it. Their great-great-grandchildren might. And that was the closest approach in 60,000 years. The average distance is 140 million miles. At that distance, a radio signal traveling at the speed of light takes up to 22 minutes to arrive. A round-trip conversation takes 44 minutes minimum. If something goes wrong on Mars and you call for help, the answer comes back nearly an hour later. That's not a technical limitation. That's just what the distance does. Getting there takes the better part of a year. Getting back takes another year. The time on the surface waiting for the return window adds 500 days or more. You're looking at a total mission duration of 2.5 to 3 years under the best realistic conditions with everything going right. The radiation exposure over that period exceeds current astronaut career limits by a meaningful margin. You accept that going in. You accept a statistically shorter life in exchange for going. That is the calculation Mars asks you to make, and the psychological reality of 30 months of cumulative isolation. That's not something that has ever been truly tested. Not by submarines, not by Antarctic stations, not by the 520-day Mars 500 simulation. Those participants could be reached immediately in a genuine emergency. A Mars crew cannot. The distance that makes the journey necessary is the same distance that makes them unreachable. Here's what's remarkable, though. None of that stops people from wanting to go. The same impulse that pushed humans across oceans in wooden ships with no GPS and no rescue, it doesn't stop at the edge of a hard number. Explorers have always accepted odds that looked unreasonable from the outside. The poles, the deep ocean floor, the moon. Every one of those destinations had people who looked at the risks and went anyway. Mars will be no different. People will go. The missions are being designed right now. The rockets are being built. The radiation shielding is being tested. The math is being done. But they will go, knowing what the distance means. And that's the thing that matters. Going to Mars without understanding the distance is like getting in a boat without knowing the ocean. The distance isn't a footnote, it's the central fact. It governs the fuel requirements, the travel time, the communication delay, the radiation exposure, the life support duration, the launch windows, the return constraints, and the psychological weight of the entire mission. Everything flows from the distance. Mars is not close, not in any sense that a human body would recognize as close. What it is the closest thing we have, and for the people who will make that journey, that distinction will be enough. If you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Good night, and the next time someone tells you Mars is just around the corner, you'll know exactly how many million miles that corner actually is.